Welcome to This Explainer. Today, we're diving into a genuinely fascinating approach to modern engineering and medicine. We're exploring the ongoing projects of the Mechatronics and Artificial Intelligence in Medicine Laboratory, better known as MAIM Lab, over at the University of Dhaka. We're going to see how they're completely rethinking how advanced technology is actually built. They're proving that, hey, you don't always need massive budgets or hyper-complex components to create world-changing innovations. Okay, let's dive right into our agenda. We're going to start off with the core MAIM Lab philosophy, then look at the Flexipede, bio-inspired robot, restoring agency with their MMG headband, the IoT health twin ecosystem, wearable fetal movement monitors, and finally, wrap up with the future of cyber-physical systems. All right, Section 1. The MAIM Lab philosophy, simplifying hardware to let AI shine. So, under the principal investigation of Dr. Abhishek Kumar Ghosh, this team operates with a really clear, overarching mission, and that is to democratize advanced medical and robotic technology. They want to make it highly scalable and translatable, especially for developing economies. To really wrap our heads around their approach, I want to pose this question to you. Does advanced technology always require complex hardware? In the modern era, we kind of just assume that cutting-edge robotics or life-saving medical devices absolutely demand expensive, power-heavy physical components. But as we'll see, MAIM Lab flips that assumption entirely on its head.
Their entire methodology really hinges on this central concept: passive mechanical intelligence. Basically, this means they strategically mitigate computational complexity by relying on optimized physical designs. So instead of throwing massive computer processors at a physical problem to try and solve it, they actually design the physical shape of a robot or a sensor to do the heavy lifting naturally. By optimizing that physical interface right out of the gate, they deliberately lighten the load for the artificial intelligence downstream. It's pretty brilliant.
Moving on to Section 2, Flexipede, bio-inspired robotics featuring morphological intelligence for extreme terrain.
This brings us to the Flexipede. It's a bio-inspired modular myriapod robot. Basically, think of a mechanical centipede. It's specifically designed for highly unpredictable stochastic environments, like post-disaster rubble, where traditional wheeled or bipedal robots would literally just get stuck or fall over. And this brilliantly illustrates their philosophy in action. You see, traditional multi-legged robots dedicate multiple motors to every single joint of a leg. That's heavy, it's expensive, and it requires immense real-time computing power just to figure out how to take a single step. But the Flexipede, it uses morphological intelligence. It drastically cuts control complexity by using just a single motor to generate a continuous, propulsive walking motion for an entire module. The physical 3D printed linkages naturally create the stepping motion, which completely bypasses the need for complex software calculations.
Because they rely on this passive mechanical intelligence, using 3D printable structures alongside off-the-shelf electronics, the fabrication cost is insanely low. The primary head module, it costs approximately $58 to build. And every expansion spine module you attach behind it is just $10. I mean, this extreme affordability is a total game changer. It makes deploying entire swarms of these rescue robots economically viable for real-world disaster relief.
Section 3, Restoring Agency, MMG Headband, which focuses on non-invasive neuromuscular assistance. So shifting gears from rescue robots to human medicine, the lab is also working on restoring agency to paralyzed patients. They've engineered a non-invasive, wearable headband specifically for those suffering from severe paralysis, locked-in syndrome, or high-level spinal cord injuries. Now, traditional assistive devices usually require messy electrical gels plastered on the face or fixed cameras that completely fail if the lighting changes. Well, MAIM Lab abandoned direct electrical measurement entirely. Instead, they use Mechanomyography, or MMG, which captures the tiny physical acoustic vibrations of muscle twitches. The absolute genius here is in the hardware. They use a custom EVO polymer membrane that perfectly matches the acoustic impedance of human skin. Just by optimizing that physical barrier, they boost the clarity to an incredibly stable 26.85 decibels. That gives the system a crystal clear signal before the software even touches the data.
And because that signal is so incredibly clear, the onboard neural network can distinguish an amazing variety of eye and head movements, what we call ocular cephalic gestures. So users aren't just stuck with one or two basic inputs. They can actually perform 14 distinct gestures, like, say, combining a left blink with a right head movement. This gives severely paralyzed individuals a super rich command vocabulary to control wheelchairs or digital communications, and it's all achieved with a staggering 94% accuracy rate.
All right, Section 4, IoT Health Twin Ecosystem, exploring the fusion of multimodal IoT data.
Our third project addresses a massive flaw in modern healthcare, the fact that it's just incredibly fragmented and reactive. To combat this, the lab is developing an ecosystem designed to create a highly personalized, continuous digital health twin of a patient. Rather than relying on just a single isolated smartwatch, this architecture fuses data from 5 distinct hardware nodes. You've got a smart gait insole tracking foot pressure and balance, a smart chair tracking your spinal posture, an environment node measuring air quality and ambient noise, a wearable node tracking heart rate and oxygen, and even a smart bottle tracking your hydration levels. It's the whole shebang.
All this data feeds into what they call a synchronous flight logger for the human body, which is meant to end what researchers call biomarker myopia. Let's put that into perspective. An isolated smartwatch might alert you to a suddenly elevated heart rate, which, could mean 100 different things. But this flight logger, it can cross-reference that heart rate spike with the environment node and the smart chair, revealing the actual root cause. So it might tell you your heart rate went up because you were exposed to a sudden spike in ambient acoustic noise while exhibiting poor posture. It finally provides real, actionable context.
Section 5. Wearable fetal movement monitors. Working towards stillbirth prevention. Our final project is a truly profound international initiative aimed at stillbirth prevention. The goal here is to create a wearable device that can objectively monitor crucial fetal kicks in unconstrained at-home environments. This would completely replace the need for subjective guessing or having to schedule expensive ultrasound visits. But monitoring a baby's movement is incredibly difficult because a mother's abdomen is just full of kinetic noise, from her walking, breathing, digestion, you name it. So the crucial point is how you actually filter that noise out. Previous attempts relied heavily on accelerometers, but those get easily saturated by the mother's own movements. MAIM Lab fixed this by introducing piezoelectric diaphragms into the mix. Because of their unique physical properties, these sensors natively filter out that maternal motion artifact, directly isolating the tiny surface displacements of a fetal kick. We're talking about movements smaller than 0.5 millimeter.
By fusing acoustic sensors with these piezoelectric diaphragms, they achieved an incredible 90% overall accuracy in discriminating true fetal movements from background noise. And honestly, the best part? They discovered that by intelligently combining these specific sensors, they could actually safely remove the power-hungry accelerators altogether. This streamlines the device, saves precious battery life, and lowers manufacturing costs, all without losing an ounce of clinical fidelity.
Moving to our final section, Section 6, the future of cyber-physical systems, systemic autonomy, and strategic trajectories.
So we've seen exactly how they build these affordable, hardware-efficient prototypes. But the question is, how do they scale them into globally deployable autonomous systems? Well, the next evolutionary step is pushing advanced processing directly onto these simplified devices. By utilizing Edge AI, which is also known as TinyML, data processing happens right there on the local hardware. And this is absolutely vital. In medical emergencies, you literally cannot afford the latency of sending data to a cloud server and just waiting around for an answer. Edge AI ensures instantaneous alerts. Furthermore, techniques like unsupervised domain adaptation and federated learning mean these devices automatically adapt to a user's unique physiology while practically guaranteeing patient privacy. Since the raw, highly sensitive health data never actually leaves the device, it's incredibly secure.
If there is one core takeaway you should have from all of this incredible research, it's anchored in this very idea. The democratization of medical and robotic technology is paramount. MAIM Lab is proving day in and day out that by being incredibly clever with physical design, by letting mechanical intelligence do the hard work, we can create life-saving, highly advanced innovations that are actually affordable and accessible to everyone everywhere.
I want to leave you with this thought as we wrap up. How might hardware simplification change the devices you use every day? When we stop relying on brute force computing and start relying on intelligent physical design, the possibilities are genuinely endless. Thank you so much for joining me on this explainer to explore these amazing innovations. Keep questioning, keep learning, and I'll catch you next time.